Welcome to solverfy.
Okay, so I have a free body diagram here drawn on the left with some equations that you might need to help yourself along. But basically, this problem isn't real distinct on what it's asking as far as the translational velocity or rotational acceleration, and then also as far as how the mass is distributed in the two balls. Um, so Um, so you can, the stuff on the left, you can use it to work out your own stuff if you want, but just generically, um, the rotational acceleration, alpha, that is torque over moment of inertia, right? Over moment of inertia. And then using all the equations on the left in the free body diagram, you can sub in and say the torque is equal to the mass times g times cosine theta. Oh, sorry, that's an O there. It's cosine theta times mu times r, right? And then that is over mr squared. Okay, so that's assuming that the bowling ball, that both balls rather, all of the mass is located at the radius. So like, it's basically a hollow sphere. And if that were not the case, we'd have to be more careful in calculating our moment of inertia. But it turns out to be, well, we'll discuss the other scenario in a minute. In this formula, though, we can see that we can just cancel out these m's here, and then cancel out this squared with that r. So basically, you'll see that there's no more m dependence, and there's just an r dependence in the denominator here. So basically what that means is that, if these bowling balls are the same radius, they should have the same angular acceleration. Or sorry, if these two balls, the bowling ball and the volleyball, are the same radius, they should have the same angular acceleration. Now in practice, that's not going to happen. And the reason being is because when the bowling ball has more mass, it's going to be less. It's going to be less subject to like air resistance and any defects in the surface and stuff. So basically, the bowling ball is probably, it is going to accelerate faster in practice. But for the sake of a textbook problem, it might have the same angular acceleration. So that is assuming that the bowling ball, all the mass is located at the surface. In reality, that's not actually the case. When the bowling ball's mass is evenly distributed throughout, that actually changes our moment of inertia. So it's no longer mr squared, and instead, we have to use another factor there. We have to use another equation, and it turns out that there's just a factor in front. So there's just like a little, I don't know. I guess we'll just call it we'll call it B. All right. So realistically, there's just a factor in front of it, and that gives you a different moment of inertia for a solid sphere rather than a hollow sphere. So they'll have different moments of inertia, and then that'll make the bowling ball, harder to accelerate. So yeah. Actually, I should probably add in the value of B. B is 2/5. And the reason why that's important is because 2/5 is the ratio of the masses of the balls that you'd have to have in order for them to have the same angular acceleration. And the reality is, like, no volleyball is 40% the mass of a bowling ball. That'd be ridiculously huge for a volleyball.